Hi there. This video will see the second example of using Mohr circle to transform stresses from one orientation to another. So in this example here we have this tube made up of 1/4 of an inch thick steel plate, and you bend it and you kind of form the tube, but then you weld between this tube that's being wrapped around in the form of a tube. So that plate is welded with in a helix way. So that shape of the weld now, it's a butt weld, but it's done in a helix kind of contour. The outer diameter of the pipe is 12 inches, and it's subject to compressive force 40 kip and a torque of 80 kip/inch. And we're given the area geometry of the area properties of the cross section. So the polar moment of inertia J, 318.67 inch to the power 4, and the area is 9.228 inch square. And what we're looking for is the stresses on the weld. So it's the normal stress, which is perpendicular to the weld surface, and the shear stress, which is parallel to the weld surface. So if you think about it, this is a helix kind of line, and it's hard to do a section at it and calculate the stresses and internal forces at it. So it's easier actually to do a cut that's perpendicular to P, so a regular cut that we were doing in most of the members, and then transform whatever stresses we get out of this cut into the orientation of the weld, which is here at 22.5 degrees from the horizontal line. So that's the big kind of solution plan. Figure out the stresses at that horizontal cut and then transform it to the orientation of the weld. So if I want to find the internal stresses on the horizontal cut, I can see here that I have internal forces, a normal one of 40 kip, and it's compressive negative, and then torque is 80 kip/inch. And if I'm interested into the stresses of the weld, let's then focus on the maximum stresses that can develop in the weld. And I'm really magnifying the thickness of the plate. But if I look here at the farthest point in the section, and I represent it by a block, and this block will feel normal stress from the 40 kip axial load and axial internal force, and it will feel shear stress tau yx following my axis shown here from the twisting moment or the torque. And if I have this shaded face of the block of stresses, this is what corresponds to the cut, horizontal cut in the pipe. Then from equilibrium, I can know that the lower surface of the block have sigma y, and there is no sigma x, there is no stresses, like I'm not squeezing the pipe sideways. But there are also a bunch of shear stresses developing to be in equilibrium with tau yx that I have directly from the torque. So there will be transverse shear stress in the plane of the section that I have, and then longitudinal shear tau xy. So now let's calculate the normal stresses or axial stresses. So sigma is equal to P over A. It's axially loaded kind of a case, and P is given, area is given to us. So we'll be able to find its negative compressive stress of 4.335 ksi. Then the shear stress comes from torque, so it's Tc over J. I'm plugging in the values right away. C is half of the diameter, so I will end up here with tau yx is the same as tau xy of 1.506 ksi. If I now look at the block from kind of sideways, so I'm looking at plane stresses here, and I will see here that I have only sigma y, no sigma x, and tau xy based on the orientation I picked here is positive shear stress. It is a positive shear stress, yes, because it's kind of pulling that shape of the block into the first quadrant of the axis and the third one. So it's kind of stretching it in this direction. So now I will, if I have these stresses, now I will be able to transform these stresses following the angle of the weld of 22.5, and that will give me different set of stresses, the transformed ones, sigma x prime, sigma y prime, and tau x prime y prime. So sigma y prime is, in this case, is the stress normal or perpendicular to the weld, and then I have the shear stress here, tau x prime y prime, and then the weld itself is subject to kind of axial load in itself, the line of weld, and that's sigma x prime. So now I need to deal with Mohr circle to do that transformation of stresses. So I will plot 2 points, sigma x with negative tau xy, and sigma y with tau xy. My tau xy was positive value on the block, so I'm plotting it as negative. So if I do that with the other point that I have, and that will be the circle I'm dealing with. Next would be figuring out the rotation here of the weld is at 22.5 degrees counterclockwise, which in the circle we know it's going to be double that, so it's 45 degrees. Now I will rotate this diameter line with 45 degrees counterclockwise. The question is, where will this line be? Will it be above the sigma horizontal axis or below it? So to be like I can graphically here see, it's probably gonna be above it, but how much of above it? How far above the horizontal axis? To know that, always think about where this original line I have of stresses is at, the orientation of it, which I can know by the theta to principal stresses, or what we call here theta p. So I will deal with this, the geometry of that hatched triangle. I will first get its primary values, which is where it's sigma average, or at this point the middle of the circle. So sigma average is the average of sigma x and sigma y. I'll end up here with negative 2.17. And also I will be interested into the radius of the circle, which will be that longer side of the triangle here, r. So it will be the square root of the height of the triangle, which is basically the value of tau, and the base of the triangle, which is half of the distance between sigma x and sigma y, which is also kind of, by coincidence, it's equal to sigma average in this case, the 2.17. So I have now the primary values of the circle, of Mohr circle, and now I can figure out 2 theta p from this hatched triangle, which is tan inverse of the height of the triangle and the base of it, over the base of it. So 1.506 divided by 1.17. I will know now that this 2 theta p is equal to 34.8 degrees. And if I know that my angle to that weld surface in the Mohr circle is 45 degrees, now I know that my line of transformed stresses will be above by an alpha angle of 10.2 degrees. And then by knowing this alpha angle, I will be able to deal with this triangle and figure out the values of sigma x prime, tau x prime, y prime, and sigma y prime. So the first one, tau x prime, y prime, its value is the height of this purple hatched triangle. So it's equal to r sine alpha. So dealing with trigonometry, that will, and plugging in the values, this will give us here, it is above the horizontal axis, and above means it's clockwise. And clockwise, in this case here, if I dealing here with the axis, the face of that's dealing with, relative to sigma x, so I'm dealing with tau xy. So if tau xy in the Mohr circle is positive, then on the block it's actually negative. So this is why I'm listing here as negative. I got tau xy, then sigma x prime would equal to, relative to sigma average, I will add r cosine alpha. So sigma average, I have it as negative 2.17 plus r 2.67 times cosine the angle alpha, and we'll end up here with small value of 0.428 ksi. And then sigma y prime will be similar formula, but then sigma average minus r cosine alpha. And that will give me here negative 0.768 ksi. So I got my stress values at the weld surface. I just want to visualize it more. So that was the stress block that's given initially to us. And then when I rotated here in real life, by 22.5 degrees, that will give us that right stress block. I can see here, and initially I have no zero sigma x. Now sigma x prime is tension, it has a value. My compressive stress on the y direction increased from 4.3385 to be 4.768, and my shear stress flipped from being a positive 1.506 to be a negative 0.467. So that's the second example of using Mohr circle to transform stresses from one orientation to another. All you can see here, I always start with drawing the circle, finding the centroid sigma average, the center of the circle sigma average, finding the radius r, and plotting the plane of, the line here that corresponds to the initial stresses that I have. Find the location or orientation of that relative to the x-axis. So I'm trying to find 2 theta p, and now with that I will know now the orientation of the other line relative to the horizontal axis, and I will deal with trigonometry here to find sigma x prime, sigma y prime, and tau x prime, y prime. So it's a very systematic process, but hopefully this is a second video, it's a second practice to see how it's being done. You will know the process of dealing with Mohr circle here. All right, so I looking forward to see you in another video. Take care, stay safe, and take care of yourself and your family.